It is my special pleasure to introduce the second keynote speaker of today, Eva Marinus. Eva has a background in cognitive science and education. She's trained as a reading researcher. She did research on reading like myself. That's how we came to know each other. And the field of reading from the cognitive science perspective is very detailed theorizing and detailed empirical data. And we've always appreciated Eva's clear thinking and clear perception of the field. So we thought as she's now developed this interest in computational thinking, we thought she's just the right person to confront us with the conceptual and methodological challenges of the field. Eva also has a personal relation to computational science, to computer science, but she already told me that she's going to tell you all that. So Eva, I think I better hand over the floor to you. We are looking forward to your presentation.
Thank you very much, Karin, and also for your trust. We'll see if I can live up to that. So it looks like I've managed to share my screen. Well, thank you again for the introduction, Karin. So I'm currently in the office in Goldau in Canton, Schwyz, and I'm showing off the building. So here at the red arrow, that's where I'm based, behind those windows, nicely behind my laptop, making notes, paying attention and thinking all about this Catrobat computational thinking conference. So this is the roadmap of my presentation. So I will start by introducing myself and my background, because I think when talking about computational thinking, it needs to be clear who is doing the thinking, because we bring our own perspectives from the fields we were raised in or where we got our education. Then I'll talk a long time about definitions of computational thinking. And I thought it was really interesting that this morning Jens said, let's be easy on us what CT actually is. Well, I really enjoy trying to find out what it is and just digging in the literature and see how this concept has evolved over time. So I'll tell a lot about that. Then I move to assessments. So we have these definitions, and how do our assessments map onto these definitions? And then a little bit about teaching of computational thinking, and then I will wrap it all up. So on the same slide, I have this reference to Shoot et al. That was a review in 2017 that aimed to demystify computational thinking. And they came up with this definition, and they based it on a literature review on definitions, assessments, and interventions of CT. And I really enjoyed reading that paper, but it's also clear that in the last 4 years, new insights have risen. So to the next slide. What is this? Now I have technical problems. So to start with the introduction, so as Karin already said, I have a diverse background. I started my studies in Amsterdam, where I studied psychology, but in that time there was no bachelor degree yet. But at the end, I got away with something that's equivalent to a master of developmental psychology. After that, I worked for about a year as a school psychologist, but I missed the university. And when there was an opening of a PhD position in education, I joined the educational science department at the same University of Amsterdam. And well, in the picture you see me with this red cylinder, which contains confirmation that I had obtained my doctor's title. After that, I moved to Australia to join Macquarie University, the Center of Cognitive Science to start with. And this is where I stayed for 8 years and worked with cognitive scientists. So when we talk about computational thinking, well, not so much computational, but I learned a lot about thinking over there. So cognitive science is about how people's minds work. So it's about memory, how people acquire language, belief formation, perception and action. And within language, also how people learn to read, mathematics, and so on. So I was very happy at this cognitive science center. And then suddenly it was all over the news. I think it was from about 2014. So I had been there for 3 to 4 years, and then in the news everywhere. Coding at school, a parent's guide to English new computing curriculum. That was in 2014. And my Australian colleagues told me, well, typically in science, when something happens in England, it happens 5 years later in Australia. But here it happens within the same year. Australia introduced the digital technologies curriculum. Well, for the Dutch people amongst us in 2015, Nelly Kroes said, code moet in de klas. I think everyone can translate that. Then in 2015, we had Obama taking a code at org workshop, working with pupils. And when I came here in Switzerland, 2018, we had Frau Baer, I believe she was the Minister of Education, saying that that programming is so wichtig wie lezen und schrijven. So same level as reading and writing. Well, I have 2 more logos here from Code Club and Code.org. Everyone should learn to code. Well, and I was doing my reading research, but I thought this is very interesting. We don't have a field of research in cognitive science that looks at the cognition of coding. I got to the word of coding because it sounds nice, cognition of coding, and also because coding was like a buzzword in the media at that time. But when I started looking into the literature, I quickly noticed that actually computational thinking was more of the important term. Well, in this at this time, the Macquarie Center for Cognitive Science achieved a lot of money, and they were rebaptized into Center for Cognition and its Disorders. And what cognitive scientists do is they build cognitive models. So I thought, well, let's build a model of coding and CT. I should have read the literature a bit more, but because CT, as we all know, is a highly complex skill. It actually consists of many skills. So if we look at within CT at abstraction or pattern recognition, alone for these skills, we could build models. It's not as easy as just reading aloud words. And the other thing I thought was, well, I've been studying reading and reading acquisition. And what we know is that a lot of children struggle to learn to read. And well, we call that dyslexia. So I might as well start preparing to treat children with dyskodia, so children that struggle to learn to code. What I quickly noticed when I embarked on this field is that studying, learning, and teaching of programming CT is an interdisciplinary undertaking. So I already had like degrees and backgrounds in cognitive science and educational science and the combination of both. After doing a lot of reading, visiting conferences, I think I can say that I'm getting there with the computer science education part of this triangle. But for this part, computer science, I don't have a degree in computer science. I need to learn and I need to work with collaborators. I had a lot of collaborators, and I am having a lot at the moment, but one of the first that joined me was Astrid Zeeman. Astrid Zeeman, I thought she was quite unique. She was just finishing up her PhD at Macquarie University when I started this cognition of coding gig. And she has a master's degree in computer science, and she was finishing up a PhD degree in cognitive science. So with her, I had a common ground of cognitive science, and we started looking into the literature and then quickly discovered that there's already a lot of information on from the perspective of the psychology of programming. So my current collaborators, my colleagues, one of them is actually here in the audience, Michael Hilscher and Beat Döbeli-Honige. They both have computer science degrees, and they are also busy in the field of computer science education. So they're teaching at our Pedagogische Hochschule. And I'd like to I'm talking about challenges in conceptual and methodological challenges in CT research. Well, one of the first challenges is to bring together the different perspectives, the aims and methods of the disciplines. So one example I could give is that if we have computer science and educational studies, one of my colleagues who has a degree in computer science said to me, well, in the beginning, I thought it was interesting that all these people in education started to talk about these computer science concepts because they don't have any background in it. But then I realized how nice it is. Because when the people in education start talking about these computer science concepts, that means that they will want to integrate it. Another interesting point I found was when I compare computer science education, so that's like when computer science, educational science meet, and then cognitive science. So at the moment at our lab, we are developing computer science concept tests. So they should, for instance, measure what kind of misconceptions children hold about computer science concepts. And well, I come from the cognitive science angle. So when we prepare scratch snippets of code, we sometimes come up with really funny programs. But if we ask a question about the program, it will reveal if a child holds a misconceptions or not. My dear colleagues from the computer science perspective, they say, Eva, we cannot use these programs. They are really strange, and the children might get confused that they're so strange. But then I'm like, but in cognitive science, we use highly distorted stimuli, and we also use pseudo words like non-words to test the reading of children, and it's not a real word, but still we can use it to find something out. So these are the kind of discussions we have, and I think we need to have these discussions. It's a very exciting field to study programming, learning to program, computational thinking, and we should be humble. And I really also like this expression of Jens that we should learn before we judge, and that we should take the time to learn from each other. Okay, so I already talked about this part of the triangle, the computer science education gang. So this community, I would say, is the main forum for discussion and research of computational thinking. They have several conferences in the ACM special interest computer science education, and people I would recommend you to follow on Twitter are Mark Gustile, Katie Rich, I'll present some work from her in this presentation, Suchi Grover, who does amazing work on all levels of definitions, assessment, and teaching, and Aman Yadav, who is very keen on integrating computational thinking in broader context, so not only in computer science. And then there are outlets like Computers and Human Behavior. So this is where tests like computational thinking tests and the computational thinking scales have been published, and journals like Computers and Education, which publish a lot of reviews. So let us talk about the evolution of definitions of CT. So my second challenge that I've defined is how to define CT and how to keep track of how others have defined it. So evolution is actually a nice way to express it. One could also say there's kind of wild growth in the definition of computational thinking. So I think Jens were already covering Seymour Papert. So he was the first to mention the computational thinking and just said it's a way to foster a unique way of thinking. Then we had Jeanette Wing, who gave us a general definition and was promoting CT's importance, so the call to arms. And then after that, we see how computer science education, teaching organizations have started to make definitions. So I'll show these in a bit. So this is from the ISTA and the CSTA. And these definitions are typically based on lists of concepts and skills that together would be computational thinking. So computational thinking has for a long time been defined as a list of skills and concepts. Probably most of you are familiar with that. So I think from 2012 onwards, people started to organize these skills and concepts, and they started to do literature reviews of all the skills. And then after 2018, we see more and more efforts to unpack the CT skills and concepts into even more sub-skills. So these sub-skills like debugging and abstraction, people realize, oh, this is still very broad, and how can we implement that in teaching? So they start to unpack it even further. So I have this triangle again, and I would say that Simon Paper, it's always nice to know was really somewhere in the middle. So he was a computer scientist, but he spent so much time in schools implementing Logo. And he was also talking about the thinking and being a disciple of Piaget. I would say he was really somewhere, he had something of everything. Then Janet Wing was clearly a computer science scientist. Well, she did a call to arms, but I don't think she really had concrete ways of implementing it into teaching or in assessment. And then the ISTA, CSTA, that's clearly the computer science education community. So as promised, I will now show you examples of these listing of concepts and skills of computational thinking. This is from a recent review from Zhang and Nouri from 2019. And well, if we just look through this list, like abstraction, algorithm, data, decomposition, parallelization, testing and debugging, control structure, what I see and what people have come to realize, it's like a really mixed bag of concepts and skills. So skills we can measure. So we couldn't develop a measure of how well children do at debugging, but how to measure abstraction, that's something that needs to be unpacked. And how to measure data, what kind of data? But still, lists like these were used to give the operational definition of computational thinking. So the ISTA, I think most of you know this definition, defined computational thinking as a problem-solving process that includes, but is not limited to, so they acknowledge it will probably change, the following characteristics: formulating problems in a way that enables us to use a computer and other tools to help solve them, locally organizing and analyzing data, representing data through abstractions such as models and simulations, automating solutions through algorithmic thinking, which is a series of ordered steps, identifying, analyzing, and implementing possible solutions with the goal of achieving the most efficient and effective combination of steps and resources, generalizing and transferring this problem-solving process to a wide variety of problems. I think we all agree with what they describe, but I think what should be kept in mind is that this was formulated for teachers. And if I were a teacher without a background in computer science, I would not have a clue how to implement this in my teaching. And I think that's a problem still with a lot of curricula, that there's a lot of general definitions, but how to unpack this. But this is happening. People have started to organize and make these concepts and skill more specific. So I've already heard this morning about Brennan and Resnick. Well, I have the triangle at the bottom again. So I would say they are somewhere between computer science and educational science, but a little bit more to computer science. So Resnick is definitely a computer science guy, and Brennan has a combination of degrees. So she would do both. And well, they organized computational thinking in 3 different categories: concepts, practices, and perspectives. And I grade perspectives out because I think that they are not restricted to computational thinking. So expressing and connecting and questioning could also be done with other types of thinking or with reading. And yeah, what I like is that they distinguish between concepts and practices. So now we can talk about practices that can be measured. And with the concepts, we can start thinking, okay, sequences, but how could we measure sequence skills, or how could we measure how well children master or understand loops? Another review of of computational thinking. This review from Tang et al. Actually focused on the assessment of CT. But before they went into the assessment, they do what a lot of computational thinking researchers do. They first summarize the review, the literature on definitions. And what I like about their summary is that they say, well, there's two different perspectives in the literature on computational thinking. Some of them related to programming and computing concepts. So it's really restricted to computing and computing concepts, whereas others focus on the competences that are needed in both domain-specific knowledge and general problem-solving skills. So again, this is actually my message. So when you read a new paper about computational thinking, try to recognize what is the background of these people and what are their aims, because this explains how they define computational thinking and what they find the important skills of computational thinking. Another study, so I promised to talk about the study of Rich. So Katie Rich, she has a very interesting website, Katie the Curious. I think she just finished her PhD, and even before she started her PhD, she did literature research on learning sequences of different CT concepts. And I think this is really, really brilliant work. So I have got two examples here, one from sequence learning and one from repetition, so loops. But she did the same for variables, she did the same for debugging, and it really unpacks these concepts for teachers, or it makes a start. How can we make those general definitions concrete for people to measure it and to teach it and to use it in their classrooms? So these sequences are like, what is the easiest way to sequence and which different components belong to sequencing? So when we were developing our misconceptions test for our project, we were actually looking in this for sequencing. So what are the components of sequencing? So one of them is order. So in which order instructions are carried out, and children could have a misconception about in which order instructions are being carried out, or that it doesn't matter in which order they're being carried out. So in my triangles, he would clearly be here between computer science and educational science. And I would even move her a little bit up because he is so explicit about the different skills, so in the direction of cognitive science. So I'm now coming to, well, we've talked about the definition of computational thinking, but in the same sentence of computational thinking, we often hear programming and coding, and how to distinguish, or do we want to distinguish between these terms? So in this morning in Ferenc's presentation, I saw, we called it a PCCT, but what I try to do here is try to define, like, at least for me, how I distinguish between these concepts, because I think if we distinguish between them, we can say what we want to measure or what we want to teach. So in the literature, you will find a lot of these figures with circles. It's not really Venn diagrams, but they try to say, well, problem solving is part of CT and it's part of computing, but it's scratch fits within programming. I've tried that too, but so far it hasn't really worked out. If someone could make like a sensible, I'm looking forward to the day that someone publishes a paper where these circles, where they add up and that everyone agrees, but I think we're not there yet. And before we're there, I just stick to bullet points. So my first bullet point would be that programming can be used to practice CT. So programming is the bigger thing, and that can be used to practice CT. So in my keynote, when I talk about programming, it's not coding. Programming, the way I see it, is computational thinking and coding. And then I have defined computational thinking as the problem analysis and algorithmic thinking. And coding I see as the process of converting an algorithm, so everything that can go unplugged without a programming language, into a programming language. So to sum it all up, for me, programming, that's the big skill, is the problem analysis, the algorithmic thinking, and the coding. So putting it in a language in a certain environment, programming environment. So I've tried to bring these thoughts together in a model of programming skills. So this is works in progress, and I've now called the Ctcm, computational thinking and coding model. And it's my further attempt to organize and specify computational thinking skills. So phase one, the problem analysis, and phase two, the algorithmic thinking, I would define as computational thinking. And then programming would definitely foster CT, but CT, computational thinking, can also be practiced in isolation. And what I really liked about this conference, I already got inspired. So this morning, Sally Hogeboom asked a question to Irene Graafsma. So where does debugging belong? So up until now, I had debugging here in the third phase, so where the programming language or environment is being implemented. But I now realize, thanks to the discussion we had, that it could also be the case that an algorithm doesn't work and that people realize, oh, this algorithm isn't right yet. And that we also need a debugging or evaluation component in the second phase. I'll come back to these three phases later. So I've talked about program analysis, about algorithmic thinking, and then about coding, so converting it into a language. But before that all gets started, we need to be aware that we're in a situation where we can use computational thinking, where we can use programming. And I think Jens is an excellent example of someone who has very high computational thinking problem solution awareness. So when he is reading ancient books with Latin, he thinks, oh, I made a snap tool for that. And I can use that to decipher the code that is in this book. For me, it was on a slightly lower level that such thinking happened. So as you all know now, I used to work in Australia, and between 2013 and 2018, I was in this massive Australian hearing hub building. I was working on the third floor. And in my time that I was still a reading researcher, I took this elevator up and down from the ground floor because that's where the cafe was. And I got my cafe and my lunch to the third floor where my office was 4 or 5 times a day. And I was happily patiently waiting for those elevators. But then after 2015, I was getting into the computational thinking literature. And voila, CT was being activated. Eva was standing in front of the elevator and was suddenly wondering, why on earth are all these elevators on level 5? What kind of algorithm is in this machine? What kind of programming language are they using? So suddenly I was aware that this was a situation where I could use computation, not that I was planning to do it, but it was this awareness that was triggered. And this is something I haven't really seen in definitions of computational thinking, but what I think is very important if we want to teach, we can teach children how to analyze problems and how to do algorithmic thinking, but what we want is that they actually use it. So now the question, how narrow, broad is computational thinking and which skills are included and which ones do we want to measure and what are the best formats to measure them? So we could define it quite narrowly, so algorithmic thinking only. And this is actually some kind of bridge to the next part of my presentation, to assessments. So I think the computational thinking test is a bit more narrow in the way it operationalizes computational thinking. Then in the middle, like skills like broader CT problem analysis, awareness skills, and at the other end, well, this morning, we also had a talk that included 21st century skills by Joseph Guggemos. So should we also include skills like communication, which is done in the computational thinking skills by Korkmaz et al. So I'm coming to the third part of my presentation, assessment of CT. So in this part, I will discuss different types of assessments using the Tang et al. Review. And I will discuss 2 examples of CT assessments, like 2 tests probably most of you know, the CT test by Roman Gonzalez et al. And the CT scales by Korkmaz et al. So Tang et al. Did this very comprehensive review of types of CT assessments. And they identified 4 types. The first one was selected or constructed response tests, which they baptized traditional tests. And that's like multiple choice and or open-ended questions, usually evaluated by correctness and completeness for summative purposes. Then they had found a lot of studies with portfolio assessments. So that's like the rating of artifacts. I would say that what Ferenc showed us this morning when they were rating the artifacts on design and creativity, I think that was like an example of portfolio assessment. Then they had surveys. I grade that out again because it was more about motivations for computational thinking, not about computational thinking itself. And then they had a couple of studies that included interviews, which they said would be particularly useful for exploring how participants developed and applied CT. So some of you might have quickly calculated like the total of those percentages, and it doesn't count to 100, it counts to 96 to 69 or something, but they also counted the combinations. And if we look at the combinations, that like the most common CT assessment types are the traditional tests and the portfolio assessments. So a couple of important conclusions from the Tang et al. Review. So as I said, the majority of the tests focus on students programming. And what I probably mean, like I have given my definitions of programming in CT, is that a programming environment or a language was used in the assessment. And it was typically with traditional tests and portfolio assessments. So those surveys were used to test CT dispositions, so attitudes and motivations, and not what I just introduced, the CT problem solution awareness. I would say that could be done with interviews. And what they explicitly underlined is stressed. They said, we need more research in the reliability and validity of the tests. And that, of course, is not easy, because if you develop tests in a new field of research, like for reading, there's a lot of tests. So if you develop a new reading test, there's a lot of tests you can correlate it with and say, well, those tests measure reading. So if they correlate highly with my new test also measures reading. But with computational thinking, there's not a lot of tests around yet. So let's see how others have solved that. So let's go to the computational thinking test. I would say that Roman Gonzalez and his colleagues are really pioneers. Like everyone knows and uses this test. And they had this massive challenge. They need to define which aspect of CT are we going to measure and validate. And they actually had made some good efforts to establish content and criterion validation. So they had in their first study where they presented the test for the first time, 2015, well, they had experts look at the items they created. They removed a couple of items and they processed all the feedback and then came up with the first version, which they then validated and did some reliability tests in 2017. And indeed, they found high correlations with spatial ability, like 0.44, reasoning skills 0.44, and problem solving ability was highest. So it's clear that computational thinking has to do with problem solving. And what they wrote is, our aim was to provide a new instrument for CT measurement and additionally give evidence of the nature of CT through its associations with related constructs. And I've been thinking about this claim, and I'm not really sure how to interpret it, but I think that it's important that as a community, that we decide what the definitions are, and then we develop a measurement that we want to assess that definition. If we then find out that our test correlates with something else, I don't think we should say that computational thinking is different because what our assessment correlates with something else. I think then we should say the assessment isn't right. Then we should change the assessment so it does measure what our definition says it should measure. But again, I'm not fully sure what was meant with this statement. Then another question about computational thinking test. Is it a CTT or the ATT? So actually in their first paper, Roman Gonzalez et al. Say, we wonder whether our test is actually a CT test or just an AT test, algorithmic thinking test. And I think they were right. I think, well, the computational concept that they are measuring, testing is basic directions, loops, conditionals, functions, and parameters. So I think these are all algorithmic thinking skills. So I would agree But it's still, because they were the first to publish this test, and this test is so widely known. It's known as the CT test, but CTT. But I think everyone who is working in this field should know that it's actually the algorithmic thinking part that is being assessed. So here we have a couple of items from their test. And I think another methodological challenge is are we able to measure computational thinking independently from a programming language or environment? So there's item number 9. I would say they did a great job there. So I don't think that children would benefit if they work with Logo or with Scratch before, because it's like a unique environment that they may not, maybe if they played Pac-Man, they have an advantage. But the other item number 25, here we can see that it's very similar to Snap or Scratch. So children that would have worked in that environment before could have a major benefit. So that's something we need to take into account when we measure CT. It's not necessarily a problem when it also measures the influence of the environment. Actually, I would go so far, it's not always desirable to measure totally independent of a known environment, because if you get to more difficult algorithms, the cognitive load will go up, or you will need to allow a lot of time to train the children in a new environment before you can test them in that environment. So now I get to the computational thinking scales. So Korkmaz et al. Define CT as having the knowledge, skill, and attitudes necessary to be able to use computers in the solution of life problems for production purposes. And I think all agree that this is a much broader definition than others have used. And they also used a different range target group as for the CTT. So in their study, they used university students, and I've learned this morning that they've also applied it to slightly younger, so end of secondary school students. And the scales are based on the definitions. There are 5 scales from ISTE in 2015. So that's a different definition of the one of 2011 I showed you. So these scales are creativity, algorithmic thinking, co-creativity, critical thinking, and problem solving. And they did, as suggested by Tang et al., a range of validity and reliability tests on it. And I just want to stress, like, it's great to do these exploratory factor analyses, these confirmatory factor analyses, and just do these very good validation analyses. But you always need to keep in mind, what is the thing I'm analyzing? What is my aim? It is my aim to evaluate on this methodological level a computational thinking scale. Am I actually evaluating computational thinking? And well, they do conclude, it has been concluded that the scale is a valid and reliable measurement tool that could measure CT skills of students. Well, I would go so far that it does maybe for algorithmic thinking, but what about cooperativity? Do we want to include that in the definition of computational thinking and say, if we measure that it's part of computational thinking, or is it another 21st century scales? We already had some kind of discussion about it this morning in the parallel session where I was, and I think we kind of agreed that we could say it's actually not computational thinking scales, but computational thinking and cooperativity scales, what they've developed. So it's back to the first methodological challenge, like defining which aspect of CT is being measured and validated, and is it actually CT that is being measured? So I'm coming to the final part of my presentation, teaching CT. So I will give in this section an example of teaching research that unpacks one specific component of computational thinking. It's abstraction by Suchi Grover. I will talk a little bit more about how to use and knowledge. That sentence doesn't make sense. It's about the model I developed and how it could be used to help with programming education. And then last but not least, toward activating and measuring computational thinking problem solution awareness. I would like to make a thing to physical computing and the maker movement. So I'm a big fan of Suchi Grover because she's acting on all levels. So she was there when computational thinking got defined. She has developed a suite of assessments, like formative assessments and summative assessments. And she is really unpacking all these difficult skills that make together form computational thinking. So if you might remember, abstraction is mentioned in almost every list of computational thinking skills. And what she does is she develops teaching programs where children and students learn about the different computer science concepts that together can be built in sequences to arrive to abstraction. And I think I would recommend everyone to keep track of Suchi Grover and what she's been working on. So this specific paper was published in Computer Science Education. And here you can see how she practices all the separate skills unplugged first. So this is on the left, the swimming pool. That's a way to practice repetition. And then on the right, it's about the introduction to Boolean expressions. So she practices these skills separately, so unplugged first, before she introduces the children to Scratch, where they can then use this knowledge to build it in. And there's now preliminary evidence that it's actually better to first practice those CT skills or computer science concepts separately before using a programming environment. So now back to the computational thinking and coding model, and I'm only talking about the phases here. I'm not showing all the boxes again. So I think this model could help teachers to define in which phase the children are stuck during programming. And why is it important to know in which phase they're stuck? Because every phase requires different skills and instructions. So I've created this table, and as I said before, I think that the total skill we can refer to as programming, and that this programming could then be divided in computational things and the coding skills. And well, I wrote down the names of the phases again: problem analysis, algorithmic thinking, and applying a programming language. And then the aims of each phase. So the aim of the first phase is to understand the problem and decide on a solution. Then the aim of the second phase of algorithmic thinking would be to define this solution in a way that can be used, applied in a computational way. And then finally to convert the algorithm, so what is defined in the second phase, into a programming language or in a specific environment. So the output of the first phase is a solution at the highest level. And I'll give an example on the next slide for that. And then the output of the second level phase will be the natural language or pseudocode algorithm that can be converted into a programming language, also unplugged without any programming language. And finally, in the third phase, it would be an implementation of the solution in a specific programming language or environment. And as I said, I would give an example. So this example comes from Einfach Informatik, which was developed by Juraj Runkovic and team at ETH. And well, in this book, there's instructions on how to use Logo. And one of the assignments is to draw a snowflake with 8 branches. So in the first phase, so it would just be the problem analysis that the child, before letting the turtle draw, gets an idea, what does it need to draw actually? So 8 branches, do I want to distribute them evenly, or the student might even make a picture, draw the snowflake first, and then algorithmic thinking. So what does it mean? What exactly, which steps does the turtle need to take to draw this snowflake, and how many degrees do I need to turn? And like all of this can be done irrespective of the local environment. Like now the student would go on and implement it in Scratch, but here it happens to be Logo. So now it needs to be converted into the specific Logo language. So when you're a teacher and you're with a child and the child says the program, it doesn't work, I think it would be helpful if the teacher would interview the child to say, so what have you done? What are you trying at the moment? And then in this interview with the child, the teacher should be discovering if it's stuck in the problem analysis phase, so it doesn't get it on paper what an 8-branch snowflake looks like, or it's about the algorithmic thinking that it doesn't know how many degrees it needs to turn, or that it's just having issues with the syntax, like with the language part of Logo. So I'm getting to the final part of my presentation towards this activating and measuring CT problem solution awareness. And I think the highest level was demonstrated by Jens this morning by, well, going from Latin ancient books to finding solutions in Snap about the secret codes that are written in those books. And then there's like a lower level example of me standing in front of elevators. So I think solutions for this are definitely being found in the physical computer and maker movement. And it's also with the Pocket Code app. It's introducing children to an environment where they can create, and it's program or be programmed. And this is, well, I'm collaborating a lot with people with computer science backgrounds, and this is so important in computer science that you are able to create something. But it's also, if we just, that's the other picture I've got here, it's around us. Computing is everywhere. It's hidden everywhere. It's like the traffic is being monitored. The internet is everywhere. There's computers in cars. And how do we make children aware of this? And what I have seen so far is the physical computing and maker movement is really focusing on motivating boys and girls from a young age. And well, different devices are being made, the CO2 measurement devices, banana pianos. And this morning I saw something with a knitting machine that it's perfect. And the focus seems to be on creating a motivation whilst also using CT, AT, and coding skills. And what I would be curious to discuss is, this activating. So before students start doing this computational thinking, problem analysis, and start with algorithmic thinking and build something, create something, how do we secure transfer? How do we get away that it's nice to have a smartphone with Pocket Code. It's nice to have this experience of having built a CO2 measurement device in the classroom, or to have made a banana piano. But how do we get the children so far that in everyday life and later in their work and in school, they actually recognize those opportunities where they can engage in computational thinking? How do we secure this transfer? And then how do we measure this, of course? How do we measure that children are so aware? So I'm going to wrap up now. So I talked about 4 different challenges, 2 in the realm of conceptual and 2 in the realm of methodological challenges. So the first challenge I discussed is interdisciplinary discussions. And here I would also like to repeat what Jens said. Learn before you judge. I think we just need to take our time and respect the different disciplines and enjoy the collaboration. That's at least what I've been doing over the last few years. And I would really like to thank my collaborators. The second challenge, there's no consensus on a definition, and that definitions have been evolving. What we need to do is keep track of the literature and find a way to organize it. I really hope that with my keynote, I provided some way it could be organized. Please feel free to give make your own version out of it. You might not agree with all the organizing I did, but feel free to use it. And yeah, we need to focus on understanding the different skills and aspects of computational thinking and make explicit which ones we want to research, assess, and teach. And also when we need to read a new paper, like what aspect of CT have they been assessing or trying to teach in this research? So the first methodological challenge, defining which aspect of CT is being measured and validated. The second, measuring CT separately from a programming language or environment. So what does it mean that when like there's a high load of someone being familiar with the environment for the reliability, or what the tool is actually assessing? So on the right, I have these 3 balls. I would say the definition of CT, it's very important to have in mind which aspects we want to assess and to teach. So that's why a definition I put at the top. So it feeds into assessment and into teaching. And I think assessment and teaching have a reciprocal relation. But with assessment, I'm hesitant to put an arrow back. I think assessment should be what we want to measure and not say we change the definition because our assessment says something else. But I do think that we can learn from teachers. So I think that how CT is defined and actually used in the classroom, that we can learn from people who are in the field and are in the schools and actually implementing all these skills in their classrooms. So that's it. I would like to thank you. And well, I'm still there. So if you would like to ask questions or have comments, please send them my way.
Thank you very much, Eva. That was absolutely what I expected from you. You raised a whole range of important aspects in this field. And I totally agree with you that in an interdisciplinary field as the one we're working in now, we need to get our definitions right. We should make sure that we're roughly talking about the same things. And I think I would really be interested to hear from this audience to what extent they agree or maybe also disagree, of course, that also advances the discussion with the proposals that you made. We've already the first questions. I'm not quite sure who was first. Maybe I start with Nana Sackbauer.
Hello. My question is, how do you propose that we get computational thinking into the curricula? Because in the moment, it's just not there. Programming is in the curriculum of some schools, but computational thinking is not part of it. They just start coding.
Could I please ask which country you're?
I'm from Austria.
You're from Austria?
Yes.
I think it really depends on the country. So in England, it's computing. It's all about computational thinking. And in Australia, it's the same. And then I've noticed here in Switzerland, and it's broader. It's more like computer science. So it's not only programming, algorithm. It's also systems and data structures. So it really depends. And it's in our curriculum in Switzerland, it's also not explicit. So, but we have algorithmic thinking in there. And at the moment, I have a student who's trying to analyze. So he is looking what is written in the curriculum and how it maps onto current definitions of computational thinking. So in your case in Austria, is it not mentioned at all? Is there no problem solving, or only that they have to program?
I can give you a real context. I'm teaching in a HTL, which is a technical school, and our goal is to bring the students to be electrical engineers or computer engineers or something like that after 5 years. And in the first grade, we have first programming skills. And I worked really, really hard to get the teachers to use Scratch before they start coding with C or something like that, so that the students at least have some kind of structured picture in their mind. Because it's just not in the curriculum. We did when I went to school, we did structure diagrams and stuff like that, but it fell out of the curriculum because there's no time in there. They need to do so much stuff in that subject, so they just skipped the diagrams, the structured diagrams, and said that's not necessary, we just start coding.
Yeah, it remains a political question, but what I hope now is, because they start earlier in primary school, that in a couple of years you get students that have more of a background and have some more basis. So it's the way I define programming in my talk, I would say is everything. So it also includes computational thinking, but I'm not sure if it's allowed in your institution to interpret programming in such a broad way.
All right, Ferenc.
Thank you. Thank you very much for your talk. It was especially interesting when you made a dimension, you put the different computational thinking measures on this dimension, contrasting the computational thinking test and the computational thinking scale. And what I found is extremely interesting, and what I don't really know is, how should we imagine computational thinking? Are we looking at something from the perspective of the computer or from the perspective of the individual? Because I think that's a crucial difference between these two measures as well. So when we are talking about the computational thinking test, you yourself said that it's about loops and different commands, while when we are talking about the computational thinking scale, those are skills, those are human skills and not test skills, but both try to point to the same direction. I wonder whether you see a difference between focusing on the computer versus focusing on the human.
Well, I think the way it was operationalized in the computational thinking test, it is about skills. They talk about those categories, and those category labels might not be ideal. So they say loops, but it's more about iterative thinking. So you could rephrase that in a cognitive way. So it's also about how they label those. I think a more important difference between the assessments is that the computational thinking scales are self-assessment. And so that they're not really conducting a task, they're assessing themselves. And I had wondered if it has to do with student confidence, that the ones that are more confident just rate themselves very highly. And that's why I liked the talk this morning, where there was cross-validation between the two, and that showed that there was a correlation between how well they did on algorithmic thinking on the computational thinking test and how they assessed themselves. So that I found that was hopeful, actually.
Okay, so you think it's only about labeling, and
yeah, I think that's
okay.
Yeah.
Yep. Thanks.
Okay, yeah. Jens has raised his hand.
Just a quick question. I really, really loved your talk. It was really cool. The one thing I didn't really understand, but maybe you can just clear it up. When you talked about the phases that you're measuring, do you imagine them to be sequentially exclusive or more like layers? Could you say a little bit to that?
I love it that you asked that question. It's because with the computer scientists here at the PHSZ, I had the same discussion. I've met a lot of people with a computer science background that say, but Eva, we just start programming, we just start writing our code.
Yeah.
And then, but I said, you are so experienced, you have forgotten what it's about. So most people need to take their steps. And it's what I learned from this is in the model, I can totally imagine you oversaw it because it was quite overwhelming with all the boxes and all the colored thingies and then the phases. But Beat and Michael convinced me to add those arrows that point back. So it is iterative. So it's possible to go back between the phases, but it's something maybe I also need to find a better way to display it. But for a cognitive scientist, it's very reassuring to have all those things separate out. But I need to find something about the dynamics. So thank you again for raising that.
No, it was really, really more of a question. I didn't disagree. The question is like, how do you measure it when things go kind of happen at the same time?
I don't know.
Okay.
So I think it's everything at the same time. That would be a portfolio analysis. That's like the end product. But I find portfolio analysis very interesting, but I want to know how they get to this project. And that's why I try to isolate the different skills, so that if we can train the skills separately, then we can better understand why the portfolio product is the way it is.
Thank you.
And Engin, we still have time for your question, comment, please.
Yeah, great. Thank you very much. Yeah, thank you for this great summary and like overview and organization of that messy space that we're all in. That's also exciting because it's still informing. And my question goes in a very similar direction to Jens's. I want to build on that. So I consider myself very strongly a situated cognitivist, if you want to take certain camps in cognitive theories. And I think that thinking with tools is a very important aspect that becomes particularly stressed or important in the context of computational thinking, where I agree with you, like experts have already much more experience with working with the programming environment, but in general, we see that with children too, that the environment is a tool to think with around them, with which they can develop ideas and understanding. And my fear is that with generally trying to organize this process of computational thinking into phases, I see similarities with the scientific reasoning work, where I have more expertise in with like science inquiry work. It becomes sequentialized. And you propose, for example, a way of using or proposing, you propose a certain interpretation like for an activity where you said first pseudocode and then go to the programming environment. But I would argue, especially when you're not an expert yet, that thinking with the environment actually can help develop certain ideas and maybe even complexify certain ideas in important ways. So I was wondering what your take is on the role of a tool as an object to think with, and how that might be one of the reasons why defining computational thinking and assessing it is particularly difficult.
I find it a very interesting question, and my brain is processing it. I do think that tools can be very, very helpful. It's just we need to be careful that we don't make the tool overcomplicated, especially when it's all new for children. Like when children, I go back to my old field, when children learn to read, we start with a few letters, with small words. We don't give them the whole book at the same time. So certainly I think that environments and tools can be motivating and helpful. It just it shouldn't be too big. I think that's my current stance on it. And we can definitely, it doesn't mean that children first need to become perfect algorithmic thinking before we introduce them to Scratch or Logo at all, or whatever. But it's just, I think that the main message I had with the phases is that when you do work with the tool, keep in mind that the problem could be in different levels. It could actually be that they don't understand the syntax or which block they need to use in Scratch, that it's really something about the tool and it's not so much in the algorithmic thinking. But I've made a note about this, the comment you made, that it's about thinking with tools and that we shouldn't take it all away. So thank you so much for that comment. And I hope we can discuss more about it when we meet in the future.
Now that it gets interesting, we unfortunately really have to move on because we have a full program. Thank you very much, Eva, for this really stimulating talk. That's what we saw from the responses. Yeah, we'll have further discussions in future meetings. That's very important.